Okay, so I want you to picture this scenario. It's kind of nightmare, really.
Uh-huh.
You wake up and you're a robot. A cute, maybe slightly clumsy robot, but you're blindfolded. You've been dropped onto this grid of tiles. Somewhere in the room, there's a diamond, a huge reward. But also, somewhere, there's a pit of fire.
High stakes for a little robot.
Extremely high stakes, and here's the real kicker. You don't have a map. You don't know the rules. You don't even know if your own wheels work properly. You might try to move north, but for all you know, you slip and slide east.
You have absolutely no idea what's going on.
Nothing. You just have to move, see what happens, and, try not to melt.
That sounds terrifying, but you've just perfectly described the fundamental problem of,
Yeah.
well, of reinforcement learning.
And that's what we're here for. Welcome back to the Deep Dive. Today, we're stripping away the instruction manuals. We're looking at how artificial intelligence learns to navigate the world when it's basically flying blind.
Yeah, we're looking at lecture materials from Dr. Reza Abdali at California State University, Channel Islands, adapted from some UC Berkeley work that really get into the mechanics of this.
And it is a huge shift. I mean, usually when we talk about AI, we're talking about offline learning, where you have the map, you have the rule book, you plan everything out before you even start.
Before you take a single step. But today, we're moving to online learning. You're in the field, making decisions in real time.
So our mission today is to figure out how an agent, our little robot, figures out the world without that manual. How do you go from just bumping into walls to, I don't know, playing chess or driving a car?
Or just surviving the room without falling into the pit.
To really get how hard this is, I think we have to start with the old way. The materials call them MDPs, Markov decision processes. And in that world, you're playing God, right?
In a sense, yeah. In a classic MDP, you're given two pieces of information that you almost never get in the real world. First, you know the transition function, usually written as dollars.
The physics of the universe.
That's it. You know that if you decide to go north, there's an 80% chance you go north, a 10% chance you slip right. You know the exact probabilities.
So you can predict the future, or at least the odds of the future.
Exactly. And the second thing you have is the reward function, or dollars. You have the cheat sheet, which states are good, the diamond, and which are bad, the fire.
Okay, so if I have $2 and I have $3, I don't really need to learn anything, do I? I can just sit down with a calculator and figure it out.
That's the whole point. The old way, it's just a computation problem. You run an algorithm, like value iteration, and you plan the perfect pass before you ever move. It's like playing a video game with a strategy guide open on your lap.
But the real world doesn't give you a strategy guide. I mean, nobody handed me a handbook for the stock market.
Or for raising a toddler, for that matter. And that's where reinforcement learning, or RL, comes in. In RL, the agent is dropped in with zero knowledge. It doesn't know the physics, and it doesn't know the rewards.
So it doesn't even know that fire hurts.
Not until it touches the fire.
Right. Ouch. That seems inefficient.
It's a harsh teacher, for sure. But the setup is simple. You've got an agent and an environment. The agent takes an action move east. The environment then gives back feedback, a new state, and a reward.
So maybe you move east and find a coin, plus 10 points. Or you move east and fall in a hole, minus 100.
Right. And the key takeaway, the most important part, is that all knowledge comes from these samples of outcomes.
You can't just sit in an armchair and think your way to the solution.
Because you don't have the data to think with. You have to get your hands dirty. You have to collect samples.
Okay, so if I'm this robot, how do I even start to organize this chaos? The lecture outlines a few different strategies. The first one, model-based learning, seems like the most, logical approach.
It's a very human way of doing things.
Yeah.
Model-based learning is basically saying, okay, I don't have a map, so I'm going to draw one as I go.
You're trying to learn the physics of the world first. You want to reconstruct that too, and that Charlie we were just talking about.
Yes. You memorize your experiences. Let's say you're in state B and you try to go east. You do it 10 times.
Yeah.
8 times you land in state Z. 2 times you slip and end up in state D.
You just write that down. Okay. Going east from B, 80% chance of C. You're building a statistical model.
Yeah, and the lecture uses this great analogy with student ages in a class. Suppose you want to find the average age of students in a lecture hall, but you don't have the roster. You don't know the demographics.
I can't just calculate it. So I have to start asking people, how old are you? How old are you?
You collect samples. And if you ask enough people, your list of samples starts to look like the real demographics of that class. You've built a model.
And once you have that data, that learned model, then you can just solve it like the old days.
Exactly. You've built what's called an empirical ADP. You think, okay, based on my notebook, going east usually works. Then you run a planning algorithm on the map you just drew.
The slides walk through this with a grid world example. Episode 1. The agent is in state B. It goes east, lands in C, gets a small penalty, -1.
Just the cost of movement. Standard stuff.
Then from C, it goes east, lands in D, another -1. From D, it exits the grid and boom, gets a +10. A big win.
But here's the catch. Based on that one episode, what does the robot think?
Well, it happened once and it worked perfectly. So the robot's got to think, if I go east from B, there's a 100% chance I land in C.
It thinks the world is deterministic, that it has total control.
Which is a dangerous level of confidence to have.
It really is. It's only after a few more episodes where maybe it tries to go north but slips that the robot starts to realize, oh, wait, the world is slippery. And it refines the map.
This sounds solid, though. I mean, build a map, plan a route. But I'm guessing there's a downside. If this were the perfect solution, the lecture would have stopped right there.
The downside is the heavy lifting. Think about it. You're spending a massive amount of brain power trying to learn the exact physics of every single tile on the grid.
Right.
Do you really need to know exactly how the wind blows on every square just to find the diamond?
Probably not. I just need to know this way good, that way bad. I don't need to be a meteorologist just to walk to the store.
Precisely. Model-based learning is computationally expensive. It scales really poorly. And that brings us to the second approach.
Yeah.
Model-free learning.
This is where we stop acting like a scientist and start acting like maybe a passenger.
A passenger is a great way to put it. The lecture introduces passive reinforcement learning. Imagine our robot is strapped into a roller coaster. It has no choice in the actions.
It's just along for the ride.
It's just observing the states and rewards that fly by. And its only goal is to figure out, how good is the state I'm sitting in right now? This is called policy evaluation.
And the simplest way to do that is something called direct evaluation, which sounds, well, direct.
It is the brute force method. The robot just keeps a running tally. Every time I visited state A, what was the total reward I got after that?
So if I visit state A and eventually get 10 points, I write down 10. If I visit it again and get 8, I average them out to 9.
Simple, right. It doesn't need to know the transitions or the rewards. It just averages outcomes.
But I can hear the but in your voice. Why is this a bad idea?
It's not bad, but it's incredibly inefficient. The lecture slides have a really sharp example for this. Suppose you have state B and state E, and in your experience, both of them always lead to state C.
Okay. So functionally, they're the same. They both dump you into the exact same situation.
Logically, then, state B and state E should have roughly the same value, right? If they both lead to the same place, they're equally good or bad.
Makes sense to me.
But direct evaluation doesn't know that. It treats state B and state E as completely separate islands. It doesn't see the connection.
So even if I've visited B 100 times and know its worth, the first time I visit E, I'm starting from scratch.
Totally from scratch. It's wasting information. It's like learning that a red stove is hot, but not realizing a blue stove is also hot. You have to touch both of them separately to learn.
That's a perfect analogy. It just takes way too long.
So we need something that's fast, like model-free, but smart enough to connect the dots.
And that's where temporal difference learning comes in. TD learning.
This is where modern RL really finds its footing. It uses a concept called bootstrapping.
Which I always think of as pulling yourself up by your own bootstraps.
And in this context, it kind of means that. It means updating a guess with another guess. With direct evaluation, you have to wait until the end of the whole episode to see your final score.
Right, I have to finish the whole game to know if my first move was good.
With TD learning, you update your opinion after every single step. You say, hey, I just moved from state S to state S prime. I already have a rough guess about how good S prime is.
Because I've been there before.
Right. So you use your immediate experience, that one little reward, plus your guess about the future, to update your opinion of where you just came from. You don't wait.
So it's a running average. I'm constantly nudging my values based on the most recent step.
Yes. And the math uses a parameter called alpha, the learning rate. And I like to think of alpha as like a personality trait.
Okay, unpack that. A personality trait, like stubbornness.
Exactly. It's how much you trust the new thing you just saw versus your long-term memory. The formula is basically new estimate equals a chunk of the old estimate plus a chunk of the new sample.
So if my alpha is high,
You're very impressionable. You see one new thing and you immediately change your mind. I saw a dog bite someone, now I believe all dogs are dangerous. You forget the past quickly.
And if alpha is low,
You're stubborn. I don't care that I just got bitten. I met 1,000 nice dogs, so I'm sticking to my belief.
and the slides mention we want to start with a high alpha and lower it over time. Why?
Because when you start, your old beliefs are garbage. You know nothing, so you want to learn quickly from everything. But as you get wiser, you want to stabilize. You don't want one weird event to completely wreck your worldview.
That is surprisingly philosophical. Forget your past failures because you didn't know what you were doing back then.
It's mathematically sound life advice.
So, okay. TD learning lets us learn the value of states quickly. State A is worth 10, B is worth minus 50. But we still have a problem. There's a snag when we try to go active.
The snag is that knowing a state is good isn't enough if you don't know which button to press to get there.
Right. If I'm in a burning room, knowing the hallway is a safe state doesn't help if I don't know which door leads there. And we're model-free, remember? We don't have the physics of the doors.
There's the limitation of learning v-values, the state values.
Mhm.
If you're model-free, you can't look ahead. You can't simulate a move to see where it lands.
So how do we fix it? How does the robot actually decide what to do?
We change what we're learning. Instead of learning, how good is this state, we learn how good is taking action A while in state S.
Ah, these are the famous Q values.
Q values,
Yeah.
Q vals.
I love the visual the slides use for this. It switches from a robot watching a car to a robot just staring at a slot machine.
It's a perfect visual because a slot machine is opaque. You don't know the internal gears, the transition function, but you can learn the value of the action. Pull the lever.
If I pull the lever, I get coins. I don't need to know the physics. I just need to know that Q text slot machine text jackpot.
Exactly. By learning these Q values, a score for every action in every situation, the agent can make decisions. It just looks at its list of actions for the current state and picks the one with the highest Q number.
Okay, so now we've got Q learning, we're making choices, we're active. But now that we're in charge, we hit a new dilemma, the fundamental trade-off.
Exploration versus exploitation.
This is the part of the lecture that always feels the most human to me. It's the restaurant problem.
Oh yeah, everyone knows this one. You got a favorite restaurant. You know the burger is a solid 8 out of 10. If you go there tonight, you are exploiting your knowledge.
You're maximizing your reward based on what you already know for sure.
Right. But then there's that new place across the street you've never been. It represents the unknown.
It might be a 10 out of 10, the best meal of my life, or it might give me food poisoning, and that's exploration.
Precisely. The agent wants to maximize rewards, so its instinct is to exploit. Just do what the QV table says is best. But if it never explores, it might get stuck on a path that gives tiny coins and miss the one that leads to the giant diamond.
So how do we program curiosity into it? How do we force the robot to try the weird restaurant?
The simplest way is called Epsilon-greedy. Epsilon-greedy.
Yeah.
Basically, you flip a weighted coin,
Just for randomness.
controlled randomness, with a small probability, say 10%, that's our epsilon.
Yeah.
The robot just acts completely crazy. It ignores what it knows and picks a random action just to see what happens.
And the rest of the time, the other 90%.
It follows the policy. It exploits.
But I can see a problem here. The slides mention thrashing. If I'm that robot, and I've already learned the maze perfectly, I still have this 10% chance of banging my head into a wall for no reason.
Yeah. It effectively acts drunk 10% of the time, even after it's an expert. It's annoying, and it can be dangerous.
So the fix is to what? Lower epsilon over time.
Right. Be really curious when you're young and dumb. Be more consistent when you're wise and experienced.
Again, solid life advice from an algorithm. But is randomness the only way? It feels a bit chaotic.
There's a smarter way. We can use what are called exploration functions.
The lecture calls this optimism in the face of uncertainty.
I love that phrase. Instead of just acting randomly, you modify how you value things. You give a bonus to states you haven't visited very often.
So the robot looks at a dark, unexplored corner of the room and thinks, I don't know what's over there, so I'm just going to assume it's awesome.
Exactly. It creates a curiosity drive. The math says, if we haven't seen this state action pair enough times, treat it as high value. This pulls the agent toward the unknown.
And if it goes there and finds a pit of fire,
Then the value plummets and it won't go back. But it propagates that curiosity back through the system. It changes the behavior from just random stumbling to intentional discovery.
which feels much closer to how intelligent, biological systems actually learn. We're drawn to the unknown.
We are. We're wired for it.
So let's recap where we've been. We started with the old way offline planning, where we knew everything, $200.
Yep, the God mode.
Then we moved to online learning. We looked at building a map, which is model-based versus just learning values, model-free. We covered simple averages with direct evaluation versus step-by-step learning with TD. And finally, we used Q values to make decisions.
It's a massive toolkit. We've basically built a robot that can learn from scratch.
But looking at the very last slide, there is a reality check waiting for us.
A scale problem.
We've been talking about these little grid worlds, 4x4 squares. The real world isn't a neat little grid.
No. Think about learning to fly a helicopter, or even a video game like Pac-Man. The number of possible states is astronomical. Every single pixel change is a new state.
If you tried to make a Q table for every pixel configuration on a screen,
You'd run out of memory of the universe. You can't visit every state. You can't possibly hold a table that big.
so does RL just fail when it hits the real world?
Not at all. But it raises the final provocative thought for our listeners. The solution, and really the next frontier in this field, is generalization.
Generalization.
Think about it. If you touch a hot stove, you burn your hand.
Yeah.
Do you need to touch every other stove in the world to know that they're also bad?
No, of course not. I generalize that stove equals hot.
Exactly. You learn features.
Yeah.
Glowing red coil equals pain. In advanced RL, we don't learn a value for every single distinct state. We learn to approximate. We use functions, often neural networks, to look at a new state and say, this looks a lot like that bad situation I saw earlier, so I'm going to avoid it.
That feels like the bridge to true AI, doesn't it? It stops being a lookup table of memorized facts and starts being, well, intuition.
Precisely. It's moving from just calculation to understanding patterns.
And on that note of intuition, we're going to wrap up this deep dive. Next time you feel like you're stumbling through life without a map, just remember, you're not lost, you're just executing an exploration function.
And don't forget to lower your epsilon as you get older.
Thanks for listening, everyone. Dive deep and keep learning.
See you next time.